So in this video, I want to introduce the next force on our list of different forces we're learning about, which is going to be the force exerted by springs. So that means, normally you think of good old fashioned like a metal coiled spring, like you would, find in the cartoon mattress or something. But of course, in reality, it will turn out that many things can be thought of as having the same properties as springs. So what we're learning here isn't just limited to those kind of cartoon style metal springs, but actually applies to a lot of other things as well. But we'll get to that later. For now, we just want to learn what is the force exerted by a spring. So we previously learned about tension forces, which are pulling forces when something gets stretched out, and compression forces, which are pushing forces when something gets squished down. So the first thing to understand is that springs can exert both tension forces if they get stretched, or compression forces if they get squished. So they can be either in tension or in compression. So it's kind of like a more sophisticated version of the tension and compression forces we were learning about before. Now, the direction then of a spring force is going to be what was just described in that previous sentence. So if the spring is stretched out, it exerts a tension force to pull back. And if the spring is squished down, it exerts a compression force to push back. So that's basically the direction of the spring force. When it comes to the magnitude of the spring force, there's a formula for that. There's a few different ways sometimes that people write this formula. The way I like to write it is F equals Kx, K times X. So F there is the magnitude of the force. K is referred to as the spring constant of the spring. And this tells you, so this is just a constant value that tells you how stiff that spring is. So for instance, a spring in your mattress is quite strong, and that would have a high spring constant because it's designed to hold a large amount of weight. Whereas there's a spring, if you have a little pen where you click the end of it and it makes the tip of the pen come out, that would have a very low spring constant because it's designed to respond just to a gentle touch. So basically a high spring constant means that spring is going to be exerting a large amount of force really readily, and a small spring constant means that spring is kind of weak and won't exert as much force, all other things being equal. The other parameter that's in that equation is X. This one, you definitely want to pay attention to what exactly X means, because this is the most common thing people get wrong when trying to apply the idea of spring force. So X is basically the displacement of the end of the spring from its natural length, from its kind of natural length where it is happy and exerts no force. This length is called the rest length of the spring. So in other words, a spring has a certain length where it is neither stretched nor compressed. Let me write that down actually, because that's kind of the simplest definition. So rest length is the length at which the spring is neither stretched nor compressed. Okay, so that's like the regular length of the spring when there's no forces on it and it's just allowed to be left alone. So in other words, let me draw this. This is a little bit, this is getting a little bit maybe too abstract with all these words and things. Let me kind of show it to you. So imagine that we have like fixed wall over here, like a vertical wall. And attached to that wall, I anchor a spring. Let me try to make that a little bit neater. And lost contact with the screen for a second. Okay, so let's say that's my spring. And let's say that I have just a box connected to the end of the spring here, just for the sake of having like an actual object that I can imagine. So I have this box at the end of the spring. So if this is just like the natural state of this spring and it's not stretched or compressed, that would be the rest length of the spring. I like to denote the rest length of the spring with a little dashed line, just to remind me where is this rest length that I'm measuring from. So imagine that now, say that's my initial state. Imagine that I have some final state down here where maybe, for example, I squish the spring down to a shorter length like that. Okay. So what I now do is I draw a displacement vector from the rest length. It has to start from the rest length. And I draw it from the rest length to the location of where the spring actually is at the moment. This is what I mean by x, and that's a vector. X is a vector. So this length here between the rest length and the actual length of the spring is what we mean by x in that formula. And conversely, if I were to, I'm kind of running out of space here, but let me see if I can squeeze another picture down at the bottom here. Let's say that we also maybe have a case where the spring now is stretched out to a really long length. Okay. In this case, the x vector would be, oops. In this case, the x vector would be like that. Okay. But the magnitude of x, could be the same either way. So the magnitude of the spring force is the spring constant times the magnitude of that x that's shown there. Remember, again, let me just say one more time, x is from the rest length to the actual length. So it has to be measured from the rest length of the spring, where the force is 0. So let's put in the force vector in these pictures. Let's say I do it in, how about green? Okay, in this second picture here, so in the first picture here, this would have F equal to 0 because it's at, remember this dashed line represents the rest length. So if it's at the rest length, X equals 0 and F equals 0. Down in the bottom, in the middle picture there, X is going to the left, the force is going to be going to the right because that guy is compressed, so it's pushing back. And then in the bottom picture, that guy is stretched out, so it's going to pull back in this direction. And so what you'll notice here is the force vector is actually always in the opposite direction from the x vector, which is why a lot of people write the spring formula in vector form as F vector equals minus k times x vector. That does not mean that the magnitude of the force is negative, of course, because that makes no sense. The magnitude of a force can never be negative. What this negative sign means is the fact that as you can see in the two pictures, the force vector and the x vector are in opposite directions, or in other words, the force always points back to the rest length. Let me write that down because that's a good thing to remember as well. That's another way to remember this. The force vector always points back toward the spring's rest length. Sometimes people call this a restoring force because the force is always acting to restore the system back to the rest length. okay? So the magnitude of the force, is K times the magnitude of X with no negative sign. The vector F is going to be K times negative X because it's times the magnitude of the X, but in the opposite direction. So that's the way that you calculate the spring force. It's actually not complicated, but you do have to be a little bit careful about it. This is yet another case where if you just see the formula F equals minus KX and just use it mindlessly, it will mislead you. But you want to actually understand what that formula means. And if you do, then it's very easy to process. Just always look for where is the rest length of the spring. Always have that in the back of your mind. Where is the rest length of this spring? Everything depends on the rest length. The direction of the force depends on the rest length, and the value of X also depends on the rest length. So if you're not looking at the rest length of the spring, you're doing something wrong. So if you just keep that in mind, you'll be in good shape with the spring force.